In this lesson, I'd like to show you that the way we represent numbers today does not actually have any effect on the way we do maths. The way we represent numbers today is largely inspired by the Hindu Arabic number system. So I've just chosen a random number here, and I've done this to show you a few of the features that our modern numbers actually have. The first of these features is that where a digit appears changes its value. So we know that this 3 over here represents 300, this 7 represents 70, and this 4 represents the number 4. Now, the idea that different places represent different values is actually a relatively recent invention. If you think about something like tally marks, if I write this, then all of them actually have the same value. This tally and this tally mean the same amount. The next feature that's also quite interesting is the inclusion of this negative sign, which indicates negation. If you take the number 374.68, negating it actually makes that into a negative number. Now, if you think of negation in terms of the numeric sets that we discussed in a previous lesson, negation actually allows us to move from the positive numbers to all the negative numbers. So in a sense, negation allows us to move from the natural numbers to the integers. Then if we take the next logical step, moving from the integers to the set of rationals requires us to include numbers that are smaller than 1, and that's the whole point of this decimal separator. Decimals allow us to represent numbers that are smaller than 1, or parts of numbers. So if this number represented some number of liters of water, we would have 374 whole liters, but then we'd also have 68 parts of 100. And then there's also one other important feature that also didn't show for a really long time, and that's the inclusion of the number 0. Now, as you know, you don't need to write any zeros here because they're implied, but the very invention of the number 0 was pretty revolutionary when it was first discovered. Now, one of the ideas here is that if this actually does represent some quantity of some physical object, then it's important to realize that the way we write this number does not change the amount of the physical object that we have. So, as we said, if this represents 374.68 liters of water, and this negative sign represents owing somebody 374.68 liters, then the amount of water that you actually owed to somebody does not change if you write this in a different way. And certainly, we've had many different number systems throughout the ages. We've written these 4s differently, we've written the zeros differently, and all kinds of things. In fact, our number system only really has digits for the numbers from 0 all the way up to 9. It doesn't really have any other digits. But historically, we've had number systems that have had different digits for numbers all the way up to, say, 60 or even 360. But this is the most important thing. The way you represent a number does not actually change the value that you're talking about. I think you realize that our modern number system has exactly 10 different digits. Many people say that that's because we have 10 fingers, but in either case, we call our number system a base 10 number system. We say that our number system is a base 10 system because each digit increases in value by 10. So for example, this 4 is worth 4, but then this 7 is worth 7 times 10, and then this 3 is worth 3 times 10 times 10, or 3 times 100. So instead of reading the 7 as the number 7, it actually means 7 times 10, or the number 70. Similarly, instead of reading this as the number 3, it's 3 times 100, or 300. Since going up requires you to multiply by 10, then going down requires you to divide by 10, and that means the next number, the 6, actually represents 6 times 1/10. So 1 part in 10 times 1 part in 10 is actually 1 part in 100. So that means this 8 actually represents 1 part in 100, all times 8. So that's 8 parts of 100. So then if you think about it, this is really just a condensed way to write out the number 300 plus 70 plus 4 plus 6 on 10 plus 8 on 100. And then, because of this minus sign, you technically have to multiply this whole number by -1. I think that when you were introduced to numbers, you were told at least quite a few times that this number over here represents the same thing as this quantity, but you were probably not shown it in this format. Now we call our system a base 10 system because it actually contains 10 different glyphs that you can use to write out the numbers. A glyph is really just a representation of a number, like this 8 over here represents the number 8. So the set of glyphs that we use today are these ones over here. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now these glyphs are really very modern, and historically we've used many other different types of glyphs. This is just what we use today. Many ancient civilizations actually used a base 60 system rather than a base 10 system, and that would mean that they actually had a set of 60 different glyphs that you had to learn if you wanted to learn to write their numbers. Now, I'd just like to give you a little bit of an unimportant but brief side note about this. If I wanted to be formal about the way we're writing numbers, like I wrote over here, then we can say that we write numbers in this format over here. This n just represents the fact that you can have -1 at the beginning, and then all of these d's actually represent the different digits. So for example, if we wanted to write this number over here in this format, we'd say that n is equal to -1 because it's a negative number. These little symbols at the bottom of the digit represent the number of zeros that they actually multiply by. So for example, D2 is the hundredths column, and that's because 100 has 2 zeros. Now the digit immediately to the left of the decimal operator, which we call D0, is actually 4 in this case. So that means D0 is equal to 4. And then the next digit is actually going to be the 7, and then the next one is going to be this 3. The digit after that, and every other digit, is actually going to be 0, because this number is actually smaller than 1000, so there's no thousands place. The digits to the right of the full stop get negative numbers, because they're actually dividing by tens rather than multiplying by them. This one is -2 because we're dividing by 2 tens, or 100. Or to make it more clear, we're dividing by a number that has 2 zeros. So that means that this digit represents the 6, and this digit just represents the 8. Now, for a number to make sense, we have to define a base system. So in our case, we're going to define the base 10 numbers. It's going to have the glyphs that we talked about over here. Now, if we use those set of glyphs, we're saying that every single one of these d's has to be inside that set of glyphs. I wrote a k over here because it can apply to any one of these digits. And then finally, you can choose n to be either 1 or -1. Now, we chose the set of glyphs to be this one over here, this g. So the cardinality of our set of glyphs is actually 10. And that means if you try comparing two digits, the value of the digit to the left is going to be 10 times larger than the digit to the right. But that only really applies if we choose base 10. Now I'm going to go ahead and make one really crazy statement. There's absolutely nothing special about base 10. So to prove this to you, I want to actually invent our own number system. Let's imagine that we had a number system that only had 3 glyphs, so it's going to be a base 3 number system. Because I'm making up a base 3 number system, I'm going to use these glyphs over here to represent the digits of our number. If we have this glyph over here, which has no triangles, that's going to represent 0. One triangle will represent the number 1, and 2 triangles will represent the number 2. Now because the cardinality of our glyph set is 3, then we can say that this is going to be a base 3 number system. Now just to show you how we'd use this, I'm going to write a particular number, and let's try to figure out what it's actually worth. So for this first digit over here, this represents the number 2, but as you know, this is just going to be the ones place, so the first digit is just worth 2. Now in a base 10 number system, the value of every digit increases by a multiple of 10. So since this is a base 3 number system, every time you go to the left by 1, you have to increase by a value of 3. And that means if this is the ones column, then this column over here is actually the threes column. And then multiplying by 3 one more time means that this column over here is actually the nines column. So if we wanted to actually read this number, this glyph represents the number 2, so we have 2 groups of 1. This glyph represents the number 0, so we have 0 groups of 3, and this glyph over here represents the number 1, so we have 1 group of 9. And that means that this funny little symbol that I've written over here is actually equivalent to the number 9 plus 2, or 11. So I find this pretty cool. If this was actually some alien number system, then you could always convert the alien numbers into our numbers just by knowing the number of glyphs in the alien language. But the other thing that's actually really cool is that no maths that these aliens would do would be any different to the maths that we discovered. And I'd like to show you this with an example. So to demonstrate, I'm going to get you to add 17 and 29 by first converting them to our made-up number system. I'll start by doing this the normal way, and then we'll compare it to what would happen if we used our number system. So the addition algorithm that most people get taught at school looks a little bit like this. Usually, we'd write the 1s on top of each other, and then we'd write the 10s on top of each other. I think most of you are taught to add the 7 and the 9 first, which will give you the number 16. This is going to be the same thing as 6 plus 10, so we're going to put in one more 10. But just to help us actually do this with our own number system, I'm going to show you to do this in a slightly different way. So I've drawn out a little thing over here that looks a little bit like a clock, but it's not a clock because it only goes from 0 up to 9. I want you to imagine starting with the number 7, so you mark it out on the clock, and then you're going to take exactly 9 leaps in the forward direction. As you can see, this lands you on the number 6. Now you didn't have to start with 7. You also could have started with 9 and then taken 7 steps forward as well. That'll get you to the exact same place. In either situation, you've landed at the number 6, so that means we're going to write out the number 6 over here. And also, because you've actually crossed the 0 one time, that means your number is actually larger than 10. So that means we need to carry 1 over here. And now for the digit down here, we just repeat the same thing. Start at 1, then add 1 for this one, and then add another 2 for this 2. That'll get you to the number 4. Now that means that 17 plus 29 is the same thing as the number 46. But we said that we wanted to do this with our own number system. So that means we should actually do the same thing we did over here, but instead of writing 1 and 10, we're going to write the multiples of 3 instead. So we can see that 1 times 3 is going to be 3, 3 times 3 is 9, and then 9 times 3 is 27. I've written out 4 columns this time because we don't know how many columns we're going to need. The first thing to do is to convert each of these numbers into this representation over here. Now let's start with the number on the top first. Going from left to right, I want you to realize that 27 is actually bigger than 17, so you're definitely not going to have any 27s in this number. Because we don't have any 27s, our glyph for 0 is this circle, so that means I'm going to write this circle over here. As for the 9, however, it turns out that 9 is actually smaller than 17, so you definitely can fit a 9 in your 17. However, 9 times 2 is 18, so you can't fit 2 of them, you can only fit 1. So by writing this triangle over here, we're saying that we can fit one group of 9 inside the 17. So the first thing we should do is we should see what we have left over. So if we started with the number 17 and we took away 9, then technically we're left with the number 8, because 17 minus 9 is 8. So after this, we want to ask whether or not it's possible to actually take 3 away from this number 8. Now because 3 is smaller than 8, you definitely can take at least one 3 out of the 8. But it turns out that 3 times 2 is actually 6. 6 is still smaller than 8, so you can actually fit 2 3s inside of this number 8. Now because we've taken away 2 groups of 3, that means we've taken 6 away from this 8. And then 8 minus 6 is just the number 2. Now because we're only left with the number 2, then in the ones column, all we have to do is to put the number 2. And the glyph for the number 2 is this double triangle. Now most of the work is actually in converting these numbers into these numbers. But I just want you to see that this still represents the number 17. 1 times 2 is 2, then 2 plus 6 is 8, then 8 plus this 9 is going to be the 17 that we started with. So you can see that we're kind of just repeating these steps in the opposite order to get this number over here. Okay, then after this we should also convert the 29 as well. Now 29 is a fair bit easier to convert because you can fit a 27 inside of 29. So if we subtract 27 from 29, we'll be left with the number 2. Now 9 is actually smaller than 2, and so is 3. So that means you can't fit any 9s in and you can't fit any 3s in. And because we're left with the number 2 yet again, that means we can fit 2 inside of the ones column. So we'll go ahead and use this double triangle just like we did above. And now we're actually ready to add, but let's just check that we have the right number. this 1 over here represents 1 times 27, and then this 2 over here represents 2 times 1. So that means we have the number 27 plus 2, which of course is the same thing as 29. Okay, so now that we've represented these numbers in terms of our new number system, now we can just perform the exact same algorithm to actually add the two numbers together. So for starters, I've drawn the same clock that we used to add the numbers on the left, but instead of using the glyphs for the base 10 number system, I use the glyphs for our own made-up number system. So for starters, we begin at the ones column. We're going to add this 2 and this 2 together. Now if we do that, we're going to start over here and then take 2 steps to the right. Now as you can see, doing this leads us to fall on this symbol over here. Now since this symbol represents 1, we're going to copy that down here. And also, since we've crossed the 0, we have to also copy another one up here. Now for the 3's column, we're going to start at this symbol over here, and then we're going to walk to the right by 2. This 0 is 0, so we don't need to walk for that. So if we start here, we move to the right by 2, leading us to fall over here. Now since we made it back to 0, we're going to copy a 0 down here. But since we've done a full lap, we also have to carry a 1 up here. Now we just continue to follow the algorithm. You can see that we're starting at 1 over here and then adding another 1. So we start here and then add 1 more. After doing this, we land at the number 2, so we copy that down here. But since we didn't cross 0, we don't need to actually carry anything. And now finally, for the last column, we're just adding 0 to 1. So if we start at 0 and add 1, of course we're just going to be at 1. So we're going to copy this 1 down here. After doing this, we've ended up with this number over here. And the only real question we have is this the same number as this one on the left? So is this set of glyphs the same thing as the number 46? Well, how about we test that? I want you to realize that this 1 over here represents one group of 27. This 2 over here represents two groups of 9. 2 times 9 is 18. Now continuing through this glyph means 0, and 0 times anything is always 0, so we can ignore this column. But this glyph over here means 1, and 1 times 1 is just 1. And now here comes the cool part. I want you to notice that 27 plus 1 is 28, and 28 plus 18 is actually exactly the same thing as the number 46. So 27 plus 18 plus 1 is just 46. And if you ask me, I think that's pretty cool. We made up our own set of numbers, and by using the standard addition algorithm, we still managed to show that you still get the right answer even with this new set of numbers. Now, of course, I wouldn't recommend that you make your own set of numbers up and use them all the time, because no one else will know what you're talking about. The reason these numbers are so useful is because everybody knows them. However, I do recommend inventing your own number system with a whole bunch of different bases like base 4, base 7, or whatever you like, and then trying a whole bunch of different algorithms out, like how would multiplication work, how would division and subtraction work. Aside from this being an interesting mathematical problem, it's actually a very practical and very useful problem that we actually need to solve all the time, and I'll just talk about that briefly before ending this lesson. The last statement I want to make is that there are many practical reasons why you would actually make up your own number systems. For starters, we can talk about computers. Now, I think you realize that computers can add numbers, and the way they actually add numbers is by physically turning off or turning on different wires inside the computer. Because a wire can only be on or off, it makes sense to use a number system that only has those two states, so we use the binary number system for this. Now, you may have heard of binary before. It's just a number system that has only two glyphs. We're going to call them 0 and 1. Now, the reason we want a number system that only has two glyphs is because this corresponds directly to the computer. 0 represents a wire being off, and 1 represents a wire being on. Another very practical reason to use another number system is when you're talking about color. The usual thing to do when talking about color is to use a base 16 number system like this one over here. Because a base 16 number system needs more glyphs than the base 10 system, we actually have to invent our own glyphs. So to keep things familiar, generally we use the letters A, B, C, D, E, and F to actually represent the missing glyphs. Again, this is a base 16 number system because the cardinality of the glyph set is actually 16. there are actually 16 digits that you can use. Now, this color over here is represented by this hex number, F02226, and that's the same thing as 15,737,382. And then this color over here is represented by the hex D37900. That's actually different to this color over here, so the number is also different. And then this number over here is the same thing as 13,859,072. Now, the reason we prefer to use hexadecimal when representing color is because each pair of these hexadecimal values actually represents part of the color. So we can say that color is actually made by mixing red, green, and blue light together. That means that if we wanted to represent this particular color, these two digits represent the red, these represent the green, and these represent the blue. And that actually makes it pretty easy to read the color directly from this once you get used to it. The red is actually a pretty large number, so we can see that you have quite a lot of red in this yellow. The green is also reasonably large, so you have a bit of green. But the blue is equal to 0, so there's absolutely no blue in this yellow color. The smallest number for each channel is going to be 00, which indicates a complete absence of color. And then the largest number is going to be FF, which indicates you completely fill that channel with color. Now, if you're interested in learning more about these applications, you can definitely do that. But the main thing to understand is that writing numbers in different ways is actually incredibly useful. So therefore, I'd just like to summarize this lesson. In this lesson, we discussed a bunch of different numeric representations. We said that our number system has a few different features. You can negate numbers, you can use decimals, there are zeros, and different positions have different values. We said that our number system is a base 10 number system, and that means each of these different digits represent a different value. So this 3 represents 300, then 70, then 4. After this, we explained that there is nothing special about a base 10 number system. In fact, to prove this, we invented our own number system, and we actually used it to do some maths, and it gave the exact same answers. And then finally, we explained that there are many practical reasons why you would actually want to use different number systems, because if you do, things actually end up a little bit easier. In fact, there are some famous problems that are actually very hard to solve with a base 10 number system, but if you move to another number system, like base 7, solving it is a lot easier. Now again, I definitely recommend using the standard digits anytime you do maths. But it is a very good exercise for you to invent your own number system and to actually try doing different mathematical things with that number system. The main takeaway I want you to have from this lesson is that the way we represent a particular number is not coupled in any way to the actual value that we're representing. And because of this reason, we have changed our representation of numbers quite a few times throughout history, and you're going to learn about other representations that we actually use to do maths other than this one over here. And with this, I'd like to end this lesson on the numeric representations of different numbers. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.